So, welcome to instrumental analysis. We'll be meeting here Tuesdays and Thursdays at 1. The lab is Thursdays from 2:30 to 3:45. We may do some labs where we just give a whole day. Because this is a little more labby. So, let's see. What you need to have a calculator. I can borrow some if you need it. But, exams are going to be based off the material in the textbook. This particular class, I do open note, open book exams, just because there's a lot of reference material. There's a decent amount of looking stuff up in tables. And it's just easier to make sure that just give you access to the book than be 100% sure I included all the tables with the test. So for the first couple of weeks, we'll start with an introduction and move on to optical components. So that'll be mostly lecture stuff, and then we'll get started with lab the first couple of weeks probably.
Like basic like instruments like that.
Yeah, it's how to use and the theory behind various instruments over there. So after in the lab, so I'll go through and you can go do a tour and I can point out what we're going to use. So we'll start with some like introduction and theory in general, talk about the optical components, the parts of these instruments for a lot of them. And then we'll go into infrared. We'll start with infrared. We have a couple of labs for infrared. Then we'll move on somewhere in around week 6, we'll have our first exam. Then we'll move on to UV visible. And then Raman, mass spectrometer, GC and separations. Hopefully I will have the mass spectrometer that we have working by then. We might not. We can still do GC stuff. And then lastly, NMR. At least that's the plan. We can shuffle things around if we need to. There's just the two of you.
Are there any master?
What?
Master?
No. If there's any homework, I'll write it up and hand it to you.
Okay.
No, there's going to be minimal homework. It's mostly just lab write-ups.
Okay.
And a couple of exams. And vibes. A little bit of vibes. But that's so we will be using this textbook, Principles of Instrumental Analysis by Skoog and Haller, which has been the textbook for instrumental analysis forever and a day, apparently. I was talking with my dad and he used to use it. So we'll be talking, I guess I can, yeah, I'll start with some lecture and then we'll go tour of the lab. So we'll talk about, measurement and some introduction material, and then we'll move on to other stuff. So this is chapter 1 in the textbook. So we'll talk about sort of the general principle of an instrument. We'll discuss sort of data domains, common types of analytical techniques and their uses, the criteria that can help in your selection of analytical technique, the importance and necessity of calibration, and the relative merits of calibration curves, standard addition, and internal standard methods. Primarily, we're going to be using things that sort of correspond to calibration curves, but simple calibration curves and stuff like that. So analytical chemistry or analysis, right? This is the science of chemical measurements. So this is sort of instrumental analysis. We're analyzing things with instruments. And you can measure some chemical species or compound. You could be either measure, the analyte is the chemical species you're interested in measuring, separating, or studying. And so analytical techniques, the earliest techniques are these classical techniques, things like separations, like precipitation, extraction, distillation, qualitative measurements of things like boiling points, melting points, refractive index, color, odor, solubilities, and quantitative measurements of things like titrations and gravimetric analysis to study like how much of something is in a sample. These are traditional chemistry methods, but we're going to be talking about instrumental methods. These developed past the 1930s or so. So there's various separation techniques, things like chromatography, which is used to separate out the various parts of the sample, electrophoresis. If you're doing biology, you may have done gel electrophoresis in biology stuff. And then quantitative or qualitative studies are things like spectroscopy. You can use for both quantitative or qualitative. You can use quantitatively to identify what you're looking at, what is in this sample. And then you can do qualitative, how much of it is there. We'll be doing both of those in our first two labs in that order, qualitative and then quantitative. We'll also can look at electrochemical methods, mass spectrometry, where you separate things out based on their atomic mass, NMR, which is nuclear magnetic resonance, where you look at the interactions of the nuclei in the chemicals, and various radiochemical methods. So separation, sort of this process is you do separation, characterization, and then gravimetric or volumetric analysis. You separate things by distillation, precipitation, or extraction. You move to characterize them by colors, melting point, boiling point, solubility, odor, or optical properties. And then you can figure out the quantity by gravimetric, volumetric analysis. So here's sort of the general principle of the process of instrumental analysis. We have some system for much of instrumental analysis. We have some system understudy. We simulate it with some energy source, and we observe how it responds to get analytical information. For most of the stuff we're doing, you hit it with light, and you either see what light comes out the other side, what light, that'll be the first part we do, see what light comes out the other side. Then we can also look at what light scatters or how it responds after you excite it with like a pulse and it decays. Those would be, the spectroscopy can do things. You can look at emission of radiation. We're not really going to do much of that, but that is a thing. Primarily, we're going to look at absorption of radiation because that's just in many ways the most straightforward way to analyze things. You shine a light through it, see what gets absorbed. Scattering of radiation, Raman is a scattering measurement. Refraction of radiation, you can look at how it refracts, or diffraction of radiation. Rotation of radiation is another one that's things like the polarization can rotate. Electrically, you can look at electrical potential, electrical charge, electrical current, or electrical resistance. And then there's a few other things like mass or mass to charge ratio. This is what a mass to charge ratio is, what is being measured by a mass spectrometer. The rate of reaction, various thermal characteristics, or radioactivity. Well, radioactivity is mostly emission of radiation. And you can also, before you do this, stimulus and response sort of thing, you can separate things by chromatography. So chromatography is separating things according to some property. Usually polarization or things like that. So, emission of radiation is things like emission spectroscopy, stuff like X-ray or UV visible electron or Auger spectroscopy, fluorescence or phosphorescence and luminescence studies. Using like a black light to identify things is a very simple version of that. Don't think we actually have any setups for that though. I don't know, we might be able to do something, but I don't think, mostly we have absorption setups. So this is spectrophotometry and photometry, could be X-ray, UV, visible IR, photoacoustic spectroscopy, nuclear magnetic resonance, and electron spin resonance spectroscopy is also absorption. Though with nuclear magnetic resonance, it's absorption of radio waves, basically. Scattering is things like turbidimetry, nuclear and Raman spectroscopy. We will do. You can look at refraction, so refractometry or interferometry, and diffraction, X-ray and electron diffraction methods. I'm not going to do either of those, but if you have questions about them, I know a bit about. Oh, I guess we will be analyzing some of our absorption spectrum using interferometry to technically be correct, because we use FTIR machines. But we're not using the interferometry to tell us about the material. We're using the interferometry to separate out different wavelengths. Rotation is things like polarimetry, optical rotary dispersion, and circular dichromism. If you want to know about that, you can ask Dr. Lacani, because his PhD was on that. Specifically vibrational circular dichromism. Electrical potential is things like potentiometry and chronopotentiometry. Electrical charge is colorimetry. Electrical current is amperometry and polarography. Electrical resistance is conductometry. Mass is gravimetry, so weighing things. Mass spectrometry, spectrometry measures mass to charge ratio. Amusingly, it is not actually spectrometry. Sorry. For some reason, the rate of reaction of various kinetic studies, thermal characteristics. You can look at thermal gravimetry and tachymetry, various calorimetry things. And radioactivity is activation and isotope dilution methods. So instrumental measurements are pretty straightforward. You have some stimulus, you have a system, and you have a response. So for example, this is a fluorescence setup. You have an energy source, which is a laser, hitting a sample, which is, the example here is tonic water, because tonic water fluoresces. And then you have an optical filter with a phototransducer, and that generates a digital signal that you can use to measure how much light is being put out. So the energy source in like a photometer, it's sort of in a base. So that would be for a fluorescence setup. For a basic spectroscopy setup, your something like UV visible thing, in a photometer, your energy source, your stimulus is a tungsten lamp. Your analytical information, what you're trying to figure out is how much that light beam gets attenuated. The way you sort is you have some filter for specific wavelengths, and you detect with a photodiode, and the data domain of transduced information comes out as electrical current, and then you process it by amplifying it, digitizing it, and say putting it out on an LED display. Or more commonly these days, feeding it into a computer and recording it. So here are some examples. A photometer uses a tungsten lamp as a light source. You're attenuating the light beam. You sort with a filter. You have a photodiode to detect, and you're looking at electrical current, and then it digitizes. Atomic emission spectroscopy, you have some inductively coupled plasma, like we have above us in these. Basically, you excite it magnetically to make a plasma. You get UV visible radiation out of that. You sort it with what's called a monochromator. A monochromator is something that allows you to choose a specific wavelength to look at. There's a whole bunch of different types, which we will talk about later. But the basic idea, you can think of it as it's like a prism and you have a slit. That is one design of monochromator. It's detected with a photomultiplier tube, which is just a more sensitive way to detect photons. You get electrical current out, then you amplify it, digitize it, feed it to a digital display. Colorimeter detects the, you're analyzing the charge required to reduce or oxidize your analyte. You're sorting it with a cell potential. You have a direct current source and electrodes. A pH meter, for example, uses a sample or a glass electrode. It's measuring hydrogen ion activity. The sorter is that glass electrode. The transducer is the glass calomel electrodes, and the electrical voltage is what you get. Mass spectrometer has an ion source. You're measuring mass to charge ratio. You sort with what's called a mass analyzer, which separates out one specific mass to charge ratio. And the transducer is some electron multiplier. Basically, whenever something hits it, it throws out more electrons. And you get electrical current out. And a chromatograph with flame ionization. The energy source is a flame. You literally light your sample on fire as it comes out of the gas chromatograph. We're looking at ion concentration versus time, because the gas chromatograph separates things out, different substances over time. So the sorter is that chromatographic column. The ion concentration gives you an electrical current because you have electrodes in there. The more ions you have, you get more current, and you can measure that. The data can be encoded either electrically or non-electrically. So non-electrically, there are things like physical and chemical stuff, the position on a scale, and just numbers. Digital stuff where you actually have numbers, you can have parallel data, serial data, or a count. This is sort of types of digital data. The electrical domains, you can measure time, process things, so things like frequency, pulse width, or phase. And the analog aspects of electrical things are things like current, voltage, and charge. And often what you do is you have some device that generates a current or a voltage or a charge, and then you measure that and convert it into some digital output that you can feed into a computer and record. So measurement starts and ends in the non-electrical domain. You're getting out some number. You start with some physical or chemical properties. So often you have sort of information flow, you have some sort of physical intensity of the source, the laws of chemistry and physics determine the amount of like fluorescence intensity or output from the analyte. Then the electrical current produced is determined by the transducer transfer function, the properties of the actual transducer. The voltage that corresponds to that electrical current is determined by Ohm's law. And then the meter transfer function tells you the number that you get out. So you start with some phenomena, the fluorescence of quinine, and you end with a quantity of quinine, where there might be some calculations in there. So measurements can remain completely in the non-electrical domain. You can weigh something with an analog scale. You can measure a volume with a graduated cylinder. You can use a ruler. I didn't get quite accurate entirely non-electrically. Like this can measure length down to 0.05 millimeters, and it's a crappy bitch. Though most people these days use the electrical version with digital output of them. Instead of that, because no one likes reading the newsstands. But if you want, I can bring him a nice one with a dial. So the non-electrical domain is though where measurements start and end, because it's not electric. The physical properties are not electrical. Most measurements do go through the numbers or the quantity that you're looking for. That's not electrical. It's just a value. But usually these days we run through the electrical domain because it's just really convenient. And there are analog and digital, and time are sort of the aspects of the electrical domain that you can look at. You can study, analog values, current, voltage, and charge. Time values, things like frequency, pulse width, and phase. And digital values, count, serial data, and parallel data. So, this is sort of an analog measurement, a more digital measurement of an analog property, and then this is showing time properties on an oscilloscope, like the one over there. So analog symbols are continuous in amplitude and time. We have this is the magnitude of voltage, current, charge, or power. They are unfortunately particularly susceptible to electrical noise. What you usually do is you have some analog signal and then you convert it to a digital signal to record it digitally. So you can have voltage versus time. This is some analog processor, current versus time. Information can also be stored in the time domain. You can be interested in things about time. So the frequency is how often things are occurring. So cycles of signal per unit time. The period is the time between successive low and high transitions. And the pulse width is the time between low high and high low transitions. It's sort of what portion of pulse width is sort of a measure of what portion is up and what portion is down. So modern dimmer switches work by rapidly pulsing on and off, but changing how much of the pulse is on and how much of the pulse is off. So, and for time stuff, the amplitude is really only important due to relative to the high-low threshold, the transition. Now, frequency can have lots of information stored in it. So you can either have you can have things like a variable frequency, where frequency changes over time. Time relationships often are information of interest. And in fact, a number of the instruments we use tricks to go between the time domain and the frequency domain to collect data very quickly. And that's this Fourier transform thing. You collect data in time and then turn it into frequency information, which is what you're interested in. Now, electrical digital data can be encoded in a two-state system. It can be only high or low, on or off. And then each piece of data is a bit, a binary digit. So usually looks more like a square wave than this, but it's you can encode data that way. But you can have non-electrical and electrical data can be conveyed using numbers, and any numerical data is digital. And when you make a measurement, this can go between several domains in the course of making the measurement. So, the source intensity is some non-electrical physical property. It goes to a different physical property, the fluorescence intensity of the analyte. Then it's turned to electrical current, then to voltage, and finally the number. Generally, in instrumental analysis, your goal is a number. So some of the tools you might use that we're going to talk about. So here's a scenario. You find a man is found lying dead in his living room floor with white powder on his upper lip. The man's roommate has a prior arrest for cocaine possession. However, there's also a box of powdered donuts on the kitchen counter. So you'd like to determine whether this white powder is cocaine or, sugar from the powdered donut. So whether this powder is cocaine, if it is cocaine, whether this cocaine is in the HCl form or the free base form, because whether it's an acid or a base has distinct differences in the legal consequences of cocaine possession. The penalties for possession of the two forms are different. And if it is cocaine, whether the man died of an overdose. What concentration of cocaine is in this man's blood. So you're going to start by identifying this white powder. You'll need to use several different tools. So Fourier transform infrared spectrum of the white powder could identify whether it is cocaine based on various identifying structural components of the molecule. So fairly straightforward process. You take the white powder, you collect a sample of it, you do probably, what's it called? Well, there's this attenuated refraction, ATF, I think it's called, where basically there's a way you can easily measure things on the surface, which is great for you found some powder. It's actually how we're going to do most of our IR measurements because it's really convenient and easy to work with. FTIR would also allow you to determine the form, free base or HCl salt of the compound. So FTIR is really good for identification of materials. So qualitative identification, because IR spectra have lots of peaks and they're generally fairly unique. They're thin and unique. Not as good at quantification because the peaks are thin and sharp. It's very easy for them to change a lot in magnitude with noise. So here, for example, is the free base, the FTIR spectrum for HCl cocaine and for free base cocaine. And you can see in this range with a wave number from about 3,000 to 2,000, they're quite different. And they're probably different down here in the fingerprinty range, but it's harder to see because they're really in little spots. And this can be identified pretty quickly with databases. You take the spectrum, you run a search against a reference database, and it'll tell you what it most likely is. If you determine the powder is cocaine, you next want to measure the concentration of cocaine in the man's blood. To do that, you need to separate the rest of the stuff in the blood out from the cocaine. So you'd use some sort of chromatography technique. In this case, probably high performance liquid chromatography, which could be used to isolate the cocaine, and it would most likely be coupled with UV visible spectrometer to detect and quantify the material you're looking at. Okay. And then another option would be to extract the cocaine into an organic solvent and then use gas chromatography to isolate the cocaine. And that would be coupled with a mass spectrometer. It could be coupled with a mass spectrometer detector, which would also basically count how much cocaine there is. And you need to understand the various strengths and limitations of each technique at your disposal and what you can do with it. So FDR spectroscopy, for example, is extremely efficient in qualitative analysis. However, it's vastly inferior to UV visible spectroscopy for quantitative analysis. What makes FTIR good at qualitative analysis makes it bad at quantitative analysis. And what makes UV visible good at quantitative analysis makes it bad at qualitative analysis. Like the by itself, the UV vis spectrometer is almost useless for conducting qualitative analysis, and that's why you isolate it using the high performance liquid chromatography to conduct quantitative UV visible analysis of the sample. Because the HPLC will separate out the various compounds over time, and you can actually identify compounds about when they come out. So you have reference material for that. And thus, you just figure out how much at the peak that you know should be the cocaine. And then as you move, so this is actually from another textbook, but we'll talk about we will talk about abilities and limitations in a great number of analytical techniques. If you'd like to see this textbook, I have a copy in my office. I just stole some slides from them. So there's sort of 5 types of instruments get applied to the majority of problems or applications. These are some of the most common ones. Ultraviolet visible spectroscopy is one. FTIR, Fourier transform infrared spectroscopy, is another. Nuclear magnetic resonance spectroscopy is a third. Mass spectroscopy is a fourth. And then gas chromatography and liquid chromatography are used for separations. So UV visible spectroscopy measures electronic transitions within a molecule. FTIR spectroscopy measures vibrational frequencies associated with each bond type. So UV visible spectroscopy is about electrons moving between energy levels. FTIR, you're looking at the ways that the molecule vibrates. So it tells you a lot more information about the bonds and how they wobble and such. Raman spectroscopy also measures those vibrations. It's kind of a mirror to FTIR. The transitions that IR is good at measuring, Raman is bad at measuring, and what IR is bad at measuring, Raman is good at measuring. So they work together well. Basically, the spectrum in IR and Raman are very similar, but where IR will have a big peak, Raman will have a little peak, kind of thing. NMR spectroscopy measures the magnetic environment around each nucleus, which tells you about how the nuclei are interacting, but also how they're shielded by electrons. So it can tell you chemical information. And mass spectrometry measures the mass of various molecules, the mass to charge ratio of an ion or ion fragment. So in a lot of the ways that mass spectrometers can be set up, the way they ionize the sample, you can have ways that ionize the sample that don't really change the molecule, but you can also have ways that are more harsh and can shatter it. And you can actually, the shattering can be very helpful for identification because the pieces you get are like a fingerprint. And then gas chromatography, liquid chromatography separates or purifies the analyte from a mixture. You separate things out. So you have a mix of a whole bunch of different stuff. You're looking for something specific in that mix. You can isolate it that way. So ultraviolet UV vis spectroscopy involves the absorption of photons in the ultraviolet region from 195 to 400 nanometers, and the visible region from around 400 to 900 nanometers of the electromagnetic spectrum. We will go into this in more detail, but it's what we can see with our eyes and into the ultraviolet. We can't go super far into the ultraviolet here, because at a certain point, your sample containers in the air start absorbing the UV. So, so if you want to do high ultraviolet spectroscopy, you need a vacuum system. And these are associated with electron transitions, electrons jumping between energy levels in molecules. So in binding molecular orbits, usually bonding molecular orbits to antibonding orbits. And we expect to see absorption of light when the energy of the incident photon equals the energy required to elevate the electron from the ground state up to the excited state. But there are a bunch of other places energy can go, so you get broad peaks. UV visible peaks tend to be broad because the extra energy, there's all these vibrational and rotational transitions that are much smaller energy, but are sort of extra places the energy can go, and that broadens the peak out. And there are a lot more interactions between the absorbing species and your solvent. This can cause changes in the ground and excited states for all the transitions. But because the peaks are broad, if you're off the center of the peak a little in your measurement, it's good. You don't get a lot of change, which makes it good for doing quantitative analysis. How much? Because if you're off a little bit on a broad peak, you don't lose a lot of magnitude, so it doesn't change your answer much. So, but because these peaks are broad, it's not a great choice for doing qualitative analysis, because one broad peak and another broad peak a little bit off looks about the same. So here is the ultraviolet visible spectrum of DPK in dry acetonitrile, and here's at a concentration of 0.828 millimolar and 4.17 millimolar. And you can see the whole thing moves as the concentration increases because of interactions with the solvent. But you can still do, well, actually, I think this might be this peak getting much bigger. Also, but you could do quantitative analysis quite well. And here is different factor of the decay of a reaction product of the enzyme myeloperoxidase. And then each spectrum was generated by subtracting the spectrum in 20-second intervals from the initial MBO spectrum. And so these are sort of these are the changes. This is the actual spectrum, and these are the differences. You can see how these are changing. You can use that to study how a reaction is proceeding. Now, quantitative analysis using Beer's law is the most common application for UV visible spectroscopy. If you have a decent, good FDIR spectroscopy, you can do the same thing. Depends on the peak, but you can get decent analysis using Beer's law. And additionally, UV visible spectroscopy is very useful in monitoring the chemical kinetics of complex reactions. because it can be pretty fast. So you can also do that, you know, because you're looking at how. And then a good quality research grade spectrometer will typically be able to receive a resolution of 1 to 2 nanometers over the range from 190 to 1100 nanometers. And in 2016, that cost less than $10,000. You know, that number is out of date. I don't know where that number is today. Some things are getting cheaper, but inflation, so. Well. Now, infrared spectroscopy. When an analyte molecule absorbs infrared photons, these are much lower energy, you're not doing electrical transitions. You're generally doing vibrations or rotations of the molecule. So you go from the ground vibrational state to an excited vibrational state. And because the vibrations are a result of the bonds that exist in the molecules being studied, absorbing the absorbance of infrared energy at specific frequencies, you can deduce what types of bonds are present in the molecule. So you can help you figure out what an unknown molecule is, like the structure of some unknown molecule that you're trying to analyze. Or various other things, like, you know, how things are organized. But it's really good for identifying molecules because they have different vibrational structures. Infrared peaks are generally quite narrow. They have a baseline width of 1 to 10% of the nominal peak wavelength, which, because they're skinny, their location is very accurate. You can use that for basically fingerprinting. And an infrared spectrum technically shows a lot of these peaks, which adds to what we can learn about the analyte. And because the structural information provided, infrared spectroscopy is an excellent qualitative tool. And because of the improvements with Fourier transform infrared, you can actually use it as an effective quantitative tool as well. It's not like naturally good at it, but Fourier transform methods give you generally so much better data than other methods that you can do it. Here, for example, the molecule DPK exhibits an absorption peak at a wave number of 1,690 inverse centimeters, which is characteristic of the stretching of a bond between carbon and oxygen in the carbonyl group. So, I mean, to analyze this, there is, on this table. That's the analysis on this table for that as well. In your text, there's this giant thing, which is just various, you know, groups and molecules and where the peaks show up. You can look at it. So that particular peak corresponds to this carbonyl group. And then the two peaks at around 1,560 inverse centimeters. Here indicate a pyridyl ring, these rings. And then the peaks around 1,430 centimeters indicate an aromatic ring. Compared to UV visible, the narrowness and low absorptivities of FTIR peaks make them less useful for quantitative analysis. And a good research grade transmission FTIR instrument can be purchased in 2016 for around $30,000. And the addition of reflectance capabilities could add $5,000 to $25,000 to that price, depending on the type and quality desired. And I don't know where those numbers are today. Scientific instruments are expensive. And here, for example, is the FTIR spectrum of cocaine and freebase cocaine. And the difference is minimal. It's literally just this group here, but they're distinctly different spectra and can be identified. So here's, why we prefer UV visible for quantitative analysis compared to infrared. So if your instrument error was 0.5% in the abscissa, the signal error from FTIR would be almost 6% in quantity, but only 0.08% for UV visible. It's just the shift, a small error in frequency or wave number or wavelength, whatever, results in a much bigger error in magnitude. And a 1% error would give you a 20% signal error in FTIR, but only 0.33 for UV visible. The sharpness of the peaks in FTIR results in great resolution and great qualitative utility, but relatively poor quantitative. Quantitative utility. That's a typo. So this is sort of error. This is error in the input, in the signal, error in the measured signal. This is IR. This is UV vis. You can see why one is better for quantitative measurements. And that's probably why in the past we've had generally lousy data when doing quantitative measurements with IR. I don't know. There's probably some other issues about particular extent. And then this is also the absorbance methods for different molar absorptions. These are UV vis. This has got much bigger absorbance than in lower absorbance. That's less of an issue in what we're likely doing because we generally have pretty highish concentrations. I have to work on that. Now, nuclear magnetic resonance spectroscopy exploits a phenomenon that occurs when nuclei in an external magnetic field absorb and re-emit pulsed electromagnetic radiation. Basically, what happens is that nuclei in a magnetic field persist, and if you whack them, well, basically, you can flip them, and then they will relax back to aligning with the magnetic field. And in that process, they can emit and wobble. You can get information on them. And modern NMR methods use Fourier transforms. So the Fourier transform NMRs, you measure the emission of electromagnetic energy as nuclei relax from a magnetic excited state. And if you've ever had an MRI, you've been the sample in one of those. Because MRIs are just imaging using NMR. And we'll go into all the details when we get to NMR. So you need to be in an external magnetic field, which is why in an NMR there's that big ring, which is a giant magnet. And like FTIR, NMR is mostly used as a qualitative tool. You can use it for quantification, but it's better at qualitative measurements. FTIR gives you information about the types of bonds present in a molecule. NMR gives you information about the connectivity of the atoms in the molecule. It tells you what what nuclei are connected to other nuclei, what they're next to, basically. So in an NMR spectrum, you can differentiate the protons of a methyl CH3 group from a methylene CH2 and determine if they're adjacent to each other or further apart in the molecule. So it gives you different structural information. So what you get out of an NMR spectrum, you get the peaks measured with chemical shift. The way the peaks split has to do with what they're next to. So that's the spin-spin coupling. And then these curves here are the integration, adding up how much signal you get from each peak, which tells you how many of, how much there is of that. The integration of each signal tells us how many protons are attached to each carbon atom type. So each of these is telling you how many of that particular, how many hydrogens are attached to each carbon atom type. The splitting of signal here into a quartet tells that this methylene group is sitting adjacent to a methyl group. So the way it splits has to do with what it's sitting next to, because it has to do with interactions. And the chemical shift corresponds to the types of groups of hydrogen. This is all looking at hydrogens. So the methylene group found at 4.25 ppm exists in an electron poor environment due to the presence of the electronegative oxygen atom. These are the big, nice superconducting NMR instruments. They're expensive. They cost $250,000. Maintenance costs of $10,000 to $20,000 a year. That is not what we have. We have a crappier tabletop NMR, but tabletop NMR has maintenance costs of, I guess we should change the filter at some point. It eats electricity, minimal. The resolution's a lot lower. Well, it's lower, but it fits on a tabletop. It's not a giant superconducting magnet. You don't need to keep it super cold, things like that. So that was the big thing that happened relatively recently, was the development of these desktop NMR machines that use permanent magnets instead of superconducting magnets. Because of that, the magnets aren't as strong, so the resolution isn't as good, because it turns out NMR resolution is directly proportional to magnetic strength. But it's a whole lot cheaper and smaller and more compact. So a superconducting NMR instrument is like, a huge cylinder, this tall, this big around. The desktop one is, well, we'll go see in a little bit, is this big. And then mass spectrometry is not strictly speaking spectrometry, because it doesn't involve light, which is what the spectra part is. But we're separating things out by mass. It's fundamentally different from any of these, UV-Vis, FTIR, NMR spectroscopy, because those are all input light, look at light that comes out. While mass spectrometry is separating things out by mass to charge ratio, the relative ion abundance of the mass to charge ratio values. So the ions of the analyte can be the analyte of interest or fragments from the analyte ion gathered during the ionization process. For quantitative measurements, the analyte of interest is useful because you get how much there was. You didn't break it into pieces. For identification, for qualitative measurements, the fragments are actually quite useful, because what it fragments into works sort of fingerprint. And it's reasonably straightforward to have a machine that can switch between both types. And is pretty standard for certain types of it. And mass spectroscopy experiment can provide substantive qualitative information, and they're also good for quantitative purposes. But generally, they need to be coupled with a chromatography system to be useful for that. So we have a mass spectrometer. It is literally an add-on to a chromatograph. It's on the side. Designed to be attached to this particular gas chromatograph. So the process is you introduce your sample, you ionize it, you separate it by some selection technique, and then you detect it. And the selection technique and the ionization technique can vary. So here's an example. This is the paradox that is diethyl oxalate. We have a small amount of it here, and then these are some fragments of it, where you get fragments of that particular thing. So the daughter ions are here, and this is the parent ion. Sometimes you get the parent ion, sometimes you don't. And you can collect and store the mass spectrum of a certain compound for later comparison with an unknown substance, and know with very high certainty if they're the same. It's very good at identification. And in more general, you buy a database, because building one is, no one wants to take several thousand mass spectra to get it. And there are huge databases of stuff online, like NIST has a massive database of infrared spectra and mass for tons of things. And I've downloaded some for use in this class. But like we have databases of material for the IR spectra, for example. Here are some examples. These are mass spectra for two similar explosives. This is pyruvic acid or trinitrophenol. And then this is trinitrotoluene or TNT. One of these is a whole lot safer than the other one. And the cost of a GC mass spec system will range depending on various user selected options from around 60,000 to 120,000. And we managed to get one for free. Because the Hammond wastewater treatment plant was not needing replacing it. So we got their old one. Now, if I can get it working is another question. And a tandem liquid chromatography mass spec system is usually even more expensive, ranging from $100,000 to $250,000. And if you lack access to mass spec, you can use other tools to put things together. So NMR is very useful for determining connectivity. So you can figure things out about the fragments, FTIR, things like that. So FTR can do your own bond types, NMR can figure out connectivity, so you can combine them. And then quantity, you can figure out with meters. But often you're dealing with a mixture. So the first step is to isolate the ion. And that's what chromatography is. This is the primary technique for separating the complex mixture. The type we'll use is gas chromatography. It uses an inert gas as the mobile phase. You have a gas, helium flowing through a system, through a capillary tube that's lined with a certain material. And it makes it very easy to feed the output of a gas chromatograph into a mass spec or some other detector. And it's limited to analytes that are volatile, but a lot of what people are interested in are volatile. Liquid chromatography uses a solvent as the mobile phase, and coupling liquid chromatography with other instrument types is a lot more challenging because you've got all this solvent you have to deal with. But liquid chromatography is not limited to volatile analytes. And chromatographic instrumentation allows for the customization of analysts to be able to sort them out. But you can use different mobile phases. You can use gradients in your mobile phase, temperature gradients. Mobile phase gradients are used more in liquid. Temperature gradients are used in gas. You could have different stationary phases. You could have different detector types. You could have tandem instrument designs where you feed one instrument into another, like a GC mass spec or GC FTIR, or liquid chromatography mass spec or liquid chromatography FTIR. And here is a chromatogram demonstrating the separation of 15 different drugs. from a complex mixture. And you can see these separate out over time. And so each particular component of this mixture has a separate peak. And the area of the peak corresponds to the quantity of the material, generally. And so here's sort of a summary. Here's some NMR spectra for GBH. And here's some infrared spectra for GBH. Yeah, and I think we'll stop there for the lecture today, and then we'll go look at the stuff in the lab. So I will just